Good day everyone, my name is Professor Oduake Omo. I'll be presenting a paper on the topic titled Interval Type 2 Fuzzy Support Vector Regression in Representation of Uncertainty in a Nonlinear System. Introduction. Most times, data presented to learning algorithms are uncertain, vague, ambiguous, or noisy. This is due to machine learning models inherently exhibit nonlinearity and are represented by huge uncertainty. This problem can unfavorably misinform a learning procedure, and this can lead to less meaningful outcome. The use of fuzzy sets is important at this point in addressing this issue. Interval type 2 fuzzy logic, which is a simplified version of a type 2 fuzzy set developed by Zede in 1976, has practical application in data selection, preparation, and processing, and this can also allow more uncertainty and imprecision in the modeling of complex systems. Well, we all know interval type 2 fuzzy logic has been successfully applied in various aspects of real life in order to address uncertainty issues in control, prediction, classification, and more. In this study, we are combine interval type 2 fuzzy logic and support vector machine in order to represent uncertainty in nonlinear system adequately. The study applies interval type 2 fuzzy membership to SVR to incorporate varying inputs into learning of the decision surface and to minimize the impact of uncertainty in the data point. Our motivation is to use this combined model to reduce prediction error in modeling uncertainties in health data and to retain generalization ability of SVR on unseen data. Experimental result is tested on a cardiovascular disease dataset. Aim and objective. The aim of the study is to eliminate uncertainty in the processing stage of SVR by using interval type 2 fuzzy logic in order to address nonlinear problems. Specific objectives are the use of interval type 2 to eliminate uncertainty in the processing stage in addressing nonlinear problems. To obtain clinical data of cardiovascular disease patients from Moore et al. 2020. Then transform the data set using interval type 2 model. The transformed data set is then used by SVR model and applied to predict the shock level in cardiovascular disease patients. Then to perform classification and prediction using this combined model. Also perform performance evaluation is carried out to test the accuracy of our model. Methodology. This study intends to fuse two models, interval type 2 fuzzy logic and support vector regression for prediction problem. We obtain clinical data of cardiovascular disease patients from Moore et al. 2020. Then use interval type 2 fuzzy model to process, enhance, and transform the data set. Interval type 2 fuzzy membership is initially applied in the phase of data selection and preparation to cause varying inputs to learn decision surface and to eliminate effects of uncertainty in the data point. The generated regression model then learns from the transformed data set and is then applied to predict the shock level of cardiovascular disease patients. Classification and prediction are performed in the final stage. The performance evaluation is also carried out on the results of the model. This slide shows the interval type 2 SVR model. This slide indicates interval type 2 model used for the prediction. We have the data set, the specification that performs the membership function unit, inference engine, the knowledge base, type reduction unit, and the specification. unit. This is the SVR model as used in our work. The SVR algorithm is employed to predict shock level using this non-linear SVR model. Result and discussion. The experimental results for leveraging SVR's capability to model nonlinear relationship and interval type 2's ability to handle high level of uncertainty has been presented. The interval type 2 fuzzy model has employed in this work in order to process, enhance, and also transform the data set. The transformed data set is used by SVR for training and testing. That has all been obtained. The presented regression model learns from the transformed data set. The final stage involved classification and prediction. The effectiveness and the generalization capability of the two models have been tested on 1,000 cardiovascular disease patients. The cardiovascular disease variables are as follows: the systolic, the blood pressure, the heart rate, respiratory rate were all obtained, and the cardiovascular shock level was also established. Investigation of the performance of our model were carried out. Then statistical using performance metrics of mean average error, mean squared error, root mean squared error, and R squared were established. This slide shows the transformed cardiovascular patients' health data set for the 4 variables. This is the results. This slide shows the results of the application of interval for type 2 fuzzy logic in the processing stage of the model. Then in the plot A shows the actual and the predicted results by the application of the interval type 2 fuzzy logic. Then B shows the system's response. The C here shows the results of the fusion of these two models, the actual and predicted results. Then D so indicates the system's response. It is observed that high accuracy is obtained from SVR model since there are few and insignificant deviations between the actual and the predicted values. Also, the actual and predicted shock level for patients as well as the system response reveal the hybrid model can predict shock level with an accuracy of approximately 99%. This slide shows here shows the model's error plots for prediction problem. The B indicates the residual plots for the problem we have solved. Then the C indicates the quartile plot for the prediction problem. A for the error plot, it is observed that the evaluated results are shown that these models is highly accurate in predicting the shock level of cardiovascular disease patients with mean squared error of 0.004, root mean squared error of 0.2, mean average error of 0.016, and R squared value of 0.975. In conclusion, this paper has been able to investigate the combination of interval type 2 and SVR in prediction problem and apply the same for the prediction of shock levels in cardiovascular disease patients. By the use of this combined model, we have been able to model nonlinear relationships and be able to handle high level of uncertainty in health data. The study has indicated 99% prediction accuracy with uniform convergence, a global minimum solution, and a minimal generalization error of 0.004. The experimental results also indicates that this diffusion of these two models can achieve a high level of prediction performance and accuracy and robust generalization potential when presented with noisy data compared to individual methods. In the future, we intend to integrate other machine learning approaches for performance comparison with the current model. Also, we intend to explore fuzzy kernel methods to address the prediction problem on the same data set. Thank you.